So yeah, don't ever do this. It's stressful, but hopefully I pulled off a nice enough talk that you guys won't hate me for this. So welcome. As Marco said, I'm Gabriele. I'm a co-founder and software engineer at Buildo, which is a software development firm in Milan. We do custom tailored solutions for businesses, and we do use Scala a lot. So for this reason, I'm also pretty much involved in the Scala community and the Scala open source community. I'm co-organizer of this conference, and I'm also a metals contributor. And so today the talk is about metals, but given my perspective on what happened in the past few years in tooling, I figured it would be pretty interesting for an audience to hear about how we came to what is metals now, and how we came to this situation in the software, in the tooling for Scala. So I kind of want to give you a chronicle of events. So this is an historical perspective on tooling that starts a few years back and ends up today, and will try to give you some educated guesses for what the future will be. So as you can see, the agenda is sort of what I divided into the pre-metals age, the metals age, which is what we're in right now, and beyond. Pun absolutely intended. So if you want to talk, which is more a deep dive into metals from a purely technical point of view and architectural point of view, I can definitely recommend this talk by Olafur Geirsson, who is the main author of metals. He gave a talk recently at Scala Days, so it's very up to date. So if you're also looking for, again, a deep dive introduction into metals, that's a great talk. So first of all, a quick survey. Can I get some lights in the room, please? Mi date qualche luce in sala? Sorry. Okay, so how many of you know what metals is? Okay, so almost everybody. How many of you have tried it? Okay, good number again. How many of you use it on a daily basis? Quite a good number as well. Like I would say, like almost half of the audience. Okay, that's pretty cool. Okay, thank you. Let's start, as I was saying, with the pre-metals age. With the pre-metals age, so technically the pre-metals age starts at the beginning of time. So I decided to put a cut at some point in the past. So we're going to go back to 2013. So in 2013, something really important for the Scala world happened, which is Project Kepler. And you may know Project Kepler as macros. So macros landed in Scala 2.10. Together with Scala Reflect, which was a new API for doing compile time and runtime reflection. So this was the work of Eugene Burmako that you see here in the photo. And he was a PhD student at EPFL, and he worked on this Project Kepler and introduced the macro system in Scala, which was a pretty big milestone for Scala tooling. So right after, in 2014, a new project called Project Palladium started. So the idea of Project Palladium was that, okay, macros are great, but the API is not that easy to use. If you're using macros today, you would know that it's not exactly straightforward to get started with macros. And part of the reason for this is that the API stems directly from a compiler representation of things. So if you're not very accustomed to the internals of the compiler, and I assume that most people are not, for good reasons, it's kind of hard to get started because there are a lot of things that are a bit confusing from a user land perspective. So the idea of Project Palladium, which is now known as Scala Meta, or at the time Scala.meta, in contrast with Scala.reflect, was to provide a first principled meta-programming foundation for doing macros. So the idea was the system for macros work, but the API is not really accessible, so let's make a new API for the macros. So this was initially announced in 2014 in a talk, Scala Days, called Rethinking Scala Macros. And the last slide of that talk said this. So Palladium will make macros straightforward and portable. We will introduce a bunch of new tooling, and welcome to the future of Scala macros. So this was 2014. So This part here, in 2019, Palladium will make macros straightforward. It didn't. Okay, so it didn't happen, which is bad news. But a lot of things happened in the meantime. Scala 3 came up with a new meta-programming system. Scala Meta took a different path. What actually happened is this part here. So the new reflection and AST interpretation and persistence and tooling around it, if you pay close attention, you may see that it's not only useful for macros. It is actually pretty useful for a lot of different things. And that is essentially what happened. So it started with the motivation of macros. Macros didn't happen, but the project stayed because it was useful to do another set of toolings. So in 2015, the Scala Meta syntactic API was ready. So what is a syntactic API? So a syntactic API in Scala Meta means that you have a parser that can parse Scala programs, which is not trivial at all. Part of this is because the Scala syntax is not exactly straightforward. There's a lot of edge cases. And also, it needs to support many different dialects, such as if you are parsing an SBT file, for instance, you can have top-level definitions already, which is a slightly different syntactical program. So it handles a bunch of cases, different dialects. And also, once you parse it, you need to parse it to something, right? Typically, you parse these things to an AST, an abstract syntax tree. So Scala Meta defines what are the trees that you actually work with. And it starts completely from scratch. It's completely unrelated to the compiler trees, which are meant for a different purpose. So it defines the data structure. So Scala Meta ended up to be essentially a data project. So it defines the data structure that you want to work with when doing meta programming. And it also has a pretty printer to print this tree back. So a very cool thing of the Scala Meta parser, by the way, is that when you're parsing for a compiler, you typically only care about the AST, because what you're doing is transforming these ASTs and producing bytecode and doing some kind of analysis on those, type checking. But when you're parsing for tooling, you also care about a lot of things that you normally discard, such as comments, such as white spaces and new lines. So these things are preserved by the Scala Meta parsers, and this is a new data structure which is called tokens, which is alongside the trees, and it's able to preserve exactly what it parsed. So you can parse a program with Scala Meta and print it back, preserving the spaces and indentation and everything. So this turned out to be pretty useful, because in 2016, Olafur, who's in the picture, defended his master thesis, which is holding in the picture, which is Scala FMT itself. So Scala FMT is a code formatter for Scala that is widely known as today. It's de facto the standard solution for formatting code in Scala. And it was developed based on top of the Scala Meta syntactic API. So this is already proof that Scala Meta, that again was born as a macro project, was useful to do different things, such as a code formatter. And the cool thing about Scala FMT, it can just ignore all the parsing and materializing the data structures part, and it can only focus on printing the trees in a way that is consistent with some configuration or some wishes, such as the line length and stuff like this. And it was actually presented here metaphorically as scala-italy. It was actually in Venice at that time in 2016. So that was useful. But then Scala Meta took it a step further. So this was again about macros. It was an attempt. It was like the third attempt at doing this thing in the context of macros. And the idea was that if you want to do macros and if you want to do more complex tooling, you don't need to only know about the syntax of a program. You want to know more about a program. So you want to know whether a string of characters represents a particular symbol in the standard library, for instance. So you want to know the types, to put it bluntly. So the idea of Scala Meta syntactic API is, this version that we have right now, is that the compiler knows a lot about your code, but it knows it about life. So it just processes your code and produces whatever it's producing, bytecode or jars or whatever, and then it discards the information and reuses the information the next time it compiles. So the general idea of Scala Meta is that we can hook into this pipeline and dump a representation of your code type-checked so that it's useful in the future. So you can dump it at compilation time, and then tools can use it for doing static analysis or augmenting the editing experience, as we will see. So the idea is that you can preserve the information from the compiler and use it for something else. The format in which these The format in which these information are stored is called semantic DB. So semantic DB is a huge specification of basically the entire Scala language and Java language, which represents these data structures that are meant for consuming by external tools. So it's essentially what I've described can be summarized as this. So you have phases in the compiler. These are super sketchy phases. They are much more complicated than this, but essentially you have a phase that type checks, and after that phase, you can hook in and dump the information that you need. So what is actually needed for semantic DB and Scala Meta semantic API to work is this compiler plugin that hooks into the compiler pipeline and dumps the files that we need. Okay, so based on this, another tool was born. It was called Migrate for S for like 15 minutes. I went back and found the first commit, and I asked Olaf about this and told me, yeah, that was a horrible idea. I'm glad we didn't choose that name. But yeah, scalafix was a tool that is based on top of the Scala Meta Semantic API. Is a tool. So the idea is that scalafnt can format your code, but scalafix can actually go ahead and perform some automatic refactors given the knowledge that these semantic data give. So it was born in a slightly different context than what is probably being used right now, which was at the very beginning of the Scala Center, which is a collective effort for producing useful open source projects for the community. One of the biggest problems was like, how do we migrate to Dotty? So we need some kind of migration tool from Scala 2 to Scala 3, right? And scalafix was the answer to that. So Olafur at that time joined the Scala Center as a software engineer and started working on this thing. So speaking of this, in 2017, in November, I was giving a presentation about scalafix. The reason was that I was particularly interested in scalafix. I really like all these new tools based on Scala Meta. I contributed a few features to scalafix, and I figured I would give a presentation. So I finished my presentation, and I was thinking, OK, scalafix now has this new cool feature. That it doesn't only allow you to refactor things, but you can also detect patterns that you want using the power of the Scala Meta Semantic API, and just report this pattern to the user, because maybe a fix isn't obvious, right? So you have, OK, I don't want you to do this. I don't know how to fix it, but I definitely don't want you to do this, right? You can write your own custom rules to do this. So my question then was, OK, I would like to have these things in the editor. And the reason is that once you have them in the editor, it's much more natural to work with these things. So instead of having just errors, you may also have red squiggles coming from a custom rule that your team defined. So these tools are normally called linters or checker of some sort. But how do you integrate scalafix with an editor? So that was my question that day back in 2017. So in order to understand how to answer this question, we need to take a small step back and talk about IDEs. So the development experience of an IDE provides is integrated, right? The I stands for integrated. So the idea is that you have this software that has an editor, and that has also a bunch of features related to the language. I mean, they may be modularized and divided internally, but the experience for the final user is that you kind of have to commit to this software for doing all your work. So if you go in Scala, there is IntelliJ. If you're working with other technologies, maybe with Swift, you got Xcode, and there are a bunch of IDEs out there. But this is not the only possible architecture. So there is a different architecture that was experimented in the past in many different ways. It's nothing new, but it's essentially this. So you can separate the editor from the features, and you can have any kind of editor, so you don't care about the editor anymore. You can be any general purpose editor. It can be Notepad for what matters. And then you have the features entirely separated. And this separation is natural to model with a client-server model, in which the client is the editor, and the editor performs requests to the server, and the server answers. So a typical request could be like, give me the completions at this point, and the service is like, OK, here's the completions. So this is pretty cool, because now you can focus on either of these two things. You can be doing the editor, or you could be doing the server. The server is specific to the language, but the editor is not. So you have freedom of choice on where to focus on. And you give this freedom to the users, because if you have a common interface to communicate with this, you can essentially decouple the editor from the server. So you can work with Vim with Java, or you can work with VS Code, with TypeScript, or you can mix and match these things. The question, though, is how do we communicate between these things? So there were, of course, many different technologies out there that doing this, many different protocols, but there was no a very broad agreement in the tooling community overall. What happened in 2016 is that Microsoft tried to answer this question with what we know as LSP. So LSP is the language server protocol, and it was developed by Microsoft while they were working on TypeScript integration with VS Code. So VS Code has its own editor, but they didn't want to embed TypeScript support in VS Code. Instead, they wanted to have the TypeScript team to manage their own features. So the TypeScript compiler already provides these features, and the VS Code just wanted to consume it. So you have literally two different teams working on these things. So they come up with a protocol, and they open sourced it in partnership with Red Hat and CodeEnvy. That was in 2016, and actually in June 2016. And the cool thing about this LSP, which actually was, I think, one of the reasons why it took over, and it's going to become a standard now, is that it's extensible and negotiable. By extensible, I mean that you can implement only a subset of it. So maybe for your own language, it doesn't make sense to talk about completions, for instance, so you don't implement that. And there is a handshake step in which the client and the server agree on the features that they mutually have. And it's also extensible in the sense that it's meant for extensions, so you can provide your own custom extensions, but of course doing this drastically lowers the possibility that the client knows what to do with these extensions. But it's still possible, and Metals uses it in some form. So you can provide more features if you want. You're not bound to the list of features that a LSP has. So back to November 2017 is if you put these things together, I want to have a Scala fix in the editor, and I also know about LSP. So this happened. I don't know to this date why I took a picture of my computer. I don't know, maybe I didn't know how to take screenshots. But so this is me talking to Olafur, and I'm like, okay, I set up a basic LSP server, and I'm playing around with these things. So my idea was like to use one of the messages that you can exchange over LSP, which is a diagnostic. So the idea is to send diagnostics from the server as it was compiling and was discovering things with scala-fix to the editor. So I was like, here it is, I'm doing this. So Olafur answered, and his answer was along the lines of, yeah, this is cool, just put it under scala-meta/LSP, we should make this a project. And I was like, what do you mean scala-meta/LSP? I mean, this is scala-fix, right? Scala-meta is more like an umbrella project of things. But he was like, yeah, sure, but if you have semantic DB set up, then you can do code exploration, so you could do jump to definitions or find references. And I'm like, I didn't think of that. So apparently Olaf did, way before I did. And he had this thing in the back of his mind, and for sort of a serendipity, those things collided, and that brought us into the Metals age. So that's essentially how the project started. That was commit number 1, and we went from there. So the first thing that happened in the project was naming it. Of course, that was the hardest thing. Completions are easy. But so at some point, Olaf came up with SMLS, which I kind of objected to it. I mean, it's super easy to misspell, so I was like, maybe we should call it seamless. And at some point, we just settled on Metals, because it's Scala meta-based, meta, LS, language server, Metals. So we debated it for a while, but what actually settled was that the metals.rocks domain was available, and of course we bought it, and yeah, the name of the group was settled, and that's the name of the project. So this seems like a stupid thing, but you have to consider that this is open source volunteer work up to this point. And the point is kind of having fun, right? So if you cannot have fun with these stupid things, you're doing it wrong. So I'm really happy to work on these things in my free time. And part of the reason is that it's such an amazing group, it's such an amazing team of contributors, and we have a lot of fun doing this. So what actually started in 2018 was what I call the POC phase. So we were working on this in our spare time. Olafur did most of the work since he was very knowledgeable about Scala Meta. He had this old vision in mind. I contributed a few features. So the idea was trying to do everything. So we had like POCs of completions working after a few months, code exploration, formatting, whatever else. Like we tried to implement every single LSP features. It was like a list of checkboxes, and we tried to tick them all. So It was entirely based on contributors' free time. There was not only me and Olafur. There were a lot of other contributors that joined in over time, each one of them contributing some kind of features and collectively learning a lot of things, which was kind of the point at this stage. It totally worked, except when it didn't. It was, as you can see, as you can imagine, a bunch of people learning a thing. It doesn't really add up to nice and scalable code. So it had tests. It crashed. It used a ridiculous amount of memory. So it was fun, but it wasn't stable. Okay. So this was released as 0.1.0, which kind of signified the end of the POC phase. Because what happened is that at this stage, Olafur got the green light from the Scala Center to work on this full time, and they changed completely everything. So what happened is this. So this is the POC phase, essentially. So that was like, yeah, this is super fun. Let's implement a bunch of things. Whoop. This is some Christmas vacation. And then, boom, completions. And this is Olafur on a plane, probably doing this. And then it's like, whoop, summer. And here is when Olafur actually started working on the project. As you can see, the first thing was rm-rf. So he deleted the whole thing. It was like, yeah, that was fun, but let's actually make this work. So he basically worked on this full time since now to up to basically July when he left the Scala Center. He's now a software engineer at Twitter, working on tools. So he partially touches metals also, but yeah, it's not his main focus anymore. And now I kind of want to take you through the releases of metals and use this as an excuse to introduce you to the features of metals and to talk about how they were implemented. And we'll see how it goes. So December 7th, 2018, that was the first release after 0.1, which obviously is 0.3. I don't know what happens to 0.2. So got lost in a way. I mean, there are tags on GitHub, but it was never released. So this is the first version that you had a chance to try if you didn't want to build your own by cloning the GitHub repo. So this was released on the marketplace. It was releasing as a package, publicly available. So you could just go on VS Code and install it. So the main three features that went into this release were build import, go to definition, and accurate diagnostics. So that was like, we want to do this very focused thing. Instead of trying to do everything, we were doing just these things. So especially for the build import part, which is very undervalued, this is the part where if it doesn't work, everything else is useless, right? It's like onboarding your project onto Metals, like letting Metals know how your project is done. So in order to talk about that, we first need, actually, I'm going to show you a quick demo, and then we're going to talk about how this actually works. So, can you see my screen? Okay, great. So, let me delete a few directories, so let's reload the window. So, you are landing, you just install Metals, and this is what happens. So, Metals starts up, it takes a few seconds for the extension to activate, and what happens is like, hey, it looks like you have an SPT project. Would you like to import the build? And you import the build. So, we actually took a lot of care in refining the UX. I personally maintain the VS Code extension, and the UX, I think, is key. I mean, if you don't get that notification, if you don't click that button, you will get a ton of questions that we'll probably ask on Gitter, on everything. So this is as smooth as it can be. It's like, would you like to do everything for free magically? OK, click here. Okay. So that is not an obvious thing to do, but we work a lot on these things. So now it's done, and your project is activated. So you get a few features for free, but I only will demo the features that were in 0.3.0, which are code navigations. So the build import you just saw, it's magic, and it's behind the scenes, which is amazing. But I will talk about more about it later. What you get is you can actually jump to stuff. So if you go here, you could jump to the successful method in the Scala standard library, and you can jump to promise if you wish, and you can keep doing that because it's fun. Okay, you can also jump to definitions inside your project. So if you're doing, like this X is defined right above, so you can jump here. And you can get, as we were saying, accurate diagnostics. So diagnostics along the way of this. So you get a diagnostic from the compiler, and it's a Scala concurrent future, but we said it was a string, so yeah, we lied. So we fix this, and this goes away. So this is actually very quick because this is a small project. But a choice that we made in the very beginning was to, in order to have accurate diagnostics, we didn't go through a live compiler. So normally IDEs have this thing which is called an integration with a presentation compiler. IntelliJ ships its own. Scala-C has one. If you get diagnostics from that, you get a lot of what we consider noise. So this is a purely usability choice that has some drawbacks and some pros. But the idea is that if you do this, okay, now if you have a presentation compiler that tries to type check this, you get an error basically all over the file. Because you are like, this is not a valid program, boom, this is a big error. So what we figure is that a pro of this approach of waiting for the compiler to send you the notification is that you can control when that happens. So if I don't do anything right now, nothing happens. As soon as I save, it happens. So now it's ridiculously quick because it's incrementally compiled and it's a one-file project. But even if you wait a second, 2 seconds, you're still controlling the thing. So you're switching between two modes. I'm editing my code, I'm saving, I'm waiting for it to type check and everything is all right, and then you keep working. Of course, this thing has drawbacks. I mean, the feedback loop is lower. But we were thinking, okay, maybe in the future we'll change it, but we never did because we actually got used to this and think it's a nice trade-off. So if you never tried anything like this, please try it out if you haven't tried Metals, and let us know what you think. We think it's a good way of working, and the diagnostics are always accurate. You never get spurious errors, because these come from the compiler. So back to the presentation for a second. Maybe. Oh, it's there. OK, cool. So again, you saw the build import, and the build import was magic. So the magic behind it brings us to 2017. And in 2017, the Scala Center funded another project, which is called Bloop. So Bloop is a build server, which means is a piece of software that stays alive on your machine and provides information about builds of the very different projects that you have configured with it. And it's essentially a wrapper around Zinc, which is the incremental compiler for Scala, which is a separate project outside of the Scala compiler, which is, again, the incremental Scala compiler. So the idea of Bloop is that it is not a build tool. So you have a build tool that defines how your build is made. And then you export your build to Bloop, and Bloop knows how your build is made. And now you can just interact with Bloop for stuff like compilation, testing, and running. So the idea is to, when you're doing compilation, testing, and running, you don't want to go through the entire build tool because that cares about a lot of other things that are just getting in the way. You just want to do this real quick. So Bloop provides a CLI for doing this, which is, as opposed to SBT, where you have a lot of different concerns, it just entirely focuses on doing these things really quickly. And it's super quick, and it works really well. It was developed by Jorge Vicente Cantero, who is still the main developer of the project, which is in the photo, and at the very beginning by Martin Duhem, who then left the center. So this was, again, 2017. And around that time, and in a work that became 1.0 in 2018, Justin Kaiser, who presented yesterday, and Jorge Cantero, and also Olafur, they work on a specification that was kind of justified by the architecture that they had in mind for these things. So if you saw the problem before with LSP, you have editors communicating with language servers. But build servers, such as Bloop, have the same problem. So they need to communicate with their clients. So the general idea was like, OK, LSP solves that problem, but we don't have a protocol for build servers, which are an entirely different beast. So the idea was to apply the same concept of LSP, so it uses the same technology and the same sort of specification, but it's a new protocol. So the way this comes together is essentially this. So you have, on one side, all the editors that you can think of. So these are the editors that are today supported in Metals. So you have Vim, Emacs, Visual Studio Code, Sublime Text, Atom, and Eclipse. So yes, you can use Metals with Eclipse, and instead of using the default Eclipse features, it just talks via LSP with Metals. This is a very recent contribution. So then Metals can just communicate to the editor over LSP, and then you have a BSP integration with Bloop, and then Bloop serves as an umbrella for all the other kind of build tools that just export their build to Bloop and delegate the communication with Metals. So technically, what BSP enables is for the right-hand side of this picture to look like at the left-hand side. So you can have these things talking BSP and talking directly to metals. So that's also a possibility that Justin explained yesterday in his talk. But right now, the way this works, and the way it works in metals today, is that you go through Bloop. So you export your build configuration to Bloop, and Bloop takes care of communicating this over BSP live with metals. So the build import, for instance, works like this. So you have the editor. Metals sends a notification to the editor and says, I noticed that you're using an SBT build. Would you want to import it? So the user clicks it and communicates to Metal, yes, I want to do that. So Metals goes and spins up Bloop or connects to it if it's already running, and he asks, OK, he asks, actually, in this case, SBT to export this build to Bloop and then starts talking to Bloop. So Metals does the heavy lifting of activating the SBT plugin for Bloop for you, and then he talks to Bloop. And the questions he asks Bloop are like, OK, tell me about this build. What are the projects? Is there a project, a submodule? What are the test projects? So it asks a lot of different things. And now Metals knows the class path of your entire project, and it can actually go and index everything it needs to provide you the features that we saw before. So now we know where to jump to when you click on future. We know how to jump to when you click on a definition. And that's essentially how the whole things come together. So that was 0.3.0. So that was the first public release of Metals. Shortly after, in January 24th, 2019, so at the beginning of this year, Metals 0.4.0 was released, which introduced two great features which are incredibly interesting in their technical details. There is a blog post on the Metals website, which I recommend if you're really into these things. It explains how find references and find symbols in Workspace work very efficiently without having to store anything on disk. It just computes everything live when you spin up the project. And they implemented using Bloom filters, so it's a cool application on Bloom filters. So I invite you to check it out if this is your jam. But as you are concerned as users, so I'm going to demo these features. So we also have symbol outline and formatting, which are a bit simpler, and I actually contributed those because they're simpler. So we'll see that in a second. So find references. OK, maybe. So find references here is kind of pointless in this toy project, but the general idea is that if you have a thing like this X, that you want to know where it's used, you want to find its references. So in VS Code, you have a shortcut that does this, and maybe it should actually compile before. OK. Of course, live demo, this doesn't work, so haha. I was hitting the wrong shortcut. OK, so if you go here and you look for this X, nothing. This X doesn't really want to work. OK, so like future, here it tells you we use it here and we use it here. So it essentially tells you what a symbol it's used across your entire code base. And it's insanely fast. If you check out Olaf's talk that I mentioned before, he tries to do this thing, I think, on the ACA project looking for string, which is used in a few places. And is actually bound by the speed of the UI to update. It's crazy, insanely fast. And again, it's super interesting how this is implemented. So you can look for symbols and their usage in the code base, but then you can also look for arbitrary symbols. So if you want to know like tests, you can find this object right here. But you can also look in the dependencies. So if you add a semicolon in the end, it will just go and find everything in the dependencies. So you can jump to a dependency. So you can find anything by looking for the symbol, and Metals will actually instruct you on where to go. And the other features, well, as I said, they were a bit easier to implement and also understand, which is like formatting. This works automatically. It integrates with scala-italy. It respects the configuration that you have in your project, and it just works. I configured it to do this on save, which is a very nice workflow. And finally, the outline, which is, as you notice here, as I type things, I get this updating live. So this is the outline, and VS Code uses it in a few places. So it uses it to power the breadcrumbs here, or you can also jump to symbols in the file by doing this. So it enables a lot of movement around in the currently open buffer. And so these are the features that were introduced in 0.4, and then this brings us to probably the biggest release of Metals that kind of got everyone hyped, completions. So up to 0.4, everything was focused entirely on code navigation. So it allows you to explore your code in a static way, which is already pretty useful. You can jump around, you can search for things. But it wasn't really useful when you were editing your code. So when you were working interactively with your code base, it didn't provide completions, it didn't provide information about types. So this release was about integrating the presentation compiler of Scala-C, again, in a pretty peculiar way, as opposed to what had been done in the past in several different attempts. So I encourage, again, to check out all of our talks for the details of how this is implemented, but I would actually demo the features. And the last two features, code folding and document highlights, were actually contributed by two guys at Virtus Lab, which are Marek and Tomasz, and they are currently working full-time on Metals. So this was the first time they got introduced to the project, and they're now the most active contributors. And those were the two features that they contributed. So real quick, we'll see completions. So if you go here and you do future, you actually can do, as I said, successful, for instance. And once you complete successful, it tells you a bunch of useful things, such as the documentation for it, or it tells you the parameter that you're using. So you put something in, and now notice how I type in 42, it realizes that it's an int, and it tells me that it's an int right there. And then if I hover on top of it, it says, OK, this is successful. You resolve to a future event, and this is the same information that you can get here when you hover on. Actually, let me do this. It doesn't like X's for some reason. So you over an X, it says that it's a future event, but successful tells you something more. It gives you the symbol signature. So you can see the def with all the generics specified. It uses nice names for it. It does a lot of different things. You can still see the documentation, of course. So this is type at point completions. Also does a pretty cool thing that is if you actually want to do this. So if you want to use like instant and you haven't imported it, you can select it and imports it for you, which again is super useful to explore your code. So it doesn't only get completions from the presentation compiler, which is bound to the current scope, also uses the indexes that we built for previous features to look around for symbols that are in your workspace that you may import. And then completions have a bunch of useful, again, a bunch of useful features. So suppose you have an option of 2, and then you do a match. You can do a match exhaustive, and you get all the cases laid down for you. Or you can do something like this. You're like doing $X. Of course, you forgot to put the S in front of it. It does it for you, and you try to access something in it, and it adds the braces. So it's super smart in trying to do these things, and those are all handwritten features that were into this release. So code folding is what you expect, but it's actually a bit smart. So it figures out that these imports are all part of the same block, so it tries to do this. And then there's another feature, which is notice how, so let me actually do this. So notice how this X gets highlighted, but this X doesn't. So this is a small, neat feature, but it's actually useful when you start using it. These are two different scope. So this X is the same as this X, but this X is not. So actually, this is semantic highlighting inside the document. So we go a bit faster now because these were the big features. OK, so 0.6.0 was a big contribution from one of the two guys that I mentioned before, was Tomasz, which added support for Maven, Gradle, and Mill in a very similar way to how the SBT worked, which is a plugin that exports the build to Bloop. Metals 0.7 was a quick release that introduces a entirely new tree view, which is extremely useful. It's currently only implemented for VS Code. It's an extension on the LSP protocol. As I mentioned, it's extensible. It's free to implement for any editor that has the concept of a tree view, so a view in which you can nest things. And it allows you to explore your jars and find all the symbols inside your dependencies, which is extremely useful if you're scouting around in a dependency and you don't want to go over in GitHub. And allows you to do the same thing in your own projects, in your local project, and it allows you to see what's going on in the compilation side. So if it's compiling 1,000 projects, when the build comes up, it will tell you that, it will tell you percentages on the completions. So it's extremely useful, but it's a very UX-related features. And I will skip over the demo for this. So what happens soon, this is essentially a list of the open PRs that are right now on Metals. They're moving quickly. So debugging support was a massive work that was done by Marek, always from Virtus Lab, and it's on the Bloop side, and now we're integrating that in the Metals side. So his work was essentially to provide debugging using yet another protocol, because there's a protocol for everything. This is called the Debugging Adapter Protocol. And it is, again, by Microsoft, is separated from LSP. I think only currently VS Code implemented, but again, we hope it will become standard, and will allow you to use Metals as a debugger, using Bloop as a backend for this. Also, the Pants integration is also very interesting. Pants is a build tool used similar in a way to Blaze, although has its peculiarities, which is used and developed at Twitter. And now it integrates with Metals. There's an open PR. It uses the same kind of approach. It offloads to Bloop, the build server part. Finally, find implementation. This was a PR from 2 days ago from Tomesh, and it essentially allows you to find all the implementations given a class. So it finds the concrete implementations across your code base. So I want to take the last minutes of this talk to talk about the future. So you heard this morning Martin talk about Scala 3. So you may think, this is great, but what happens now? Where are all these tools going? So I read and I heard a lot of different opinions. Some people are extremely worried. Some people are like, OK, Scala 3 will break everything. We'll maintain compatibility with Scala 2, maybe on an application level side, but on the tooling side, it will just break everything. So I have some considerations for you related to Metals. So Scala 3 and Metals, I think, is going to be a great match for 2 reasons. These are the main 2 reasons, but there's a bunch of different reasons. So we have 2 brittle points in Metals, which are extremely fragile for different reasons. So the integration that I showed you before, in which there is a semantic Scala-C, semantic-DB Scala-C plugin that hooks into the compiler and dumps stuff in semantic-DB files, is fragile in the sense that we need to release a compiler plugin for each of every patch versions of the Scala compiler, which is tedious from a process point of view and slows down the releases of Metals itself because it's downstream. So that's the reason why we don't yet have 2.13.01 support for Metals, although I opened a PR a few days ago. But it takes a few days, which is annoying. So the other thing is that the presentation compiler in Scala 2 is a weird beast. I mean, we have a fairly good relationship in Metals with this beast, but it was not really developed with modern information that we have now about tooling. So the Dotty presentation compiler was actually developed with that in mind. And as a proof of this, the Dotty team actually implemented their own LSP server using the presentation compiler and using the Tasty integration. So these 2 things will actually get better. The semantic-DB Scala-C integration can be replaced by integrating directly with Tasty. If you don't know what Tasty is exactly the same approach that we were doing before, which is persisting stuff during the compilation, but the compiler actually does it. It's meant for binary compatibility, but it can be used, and there's a proof of concept, to produce semantic DB files. So we can just stop hooking into the compiler, and the compiler will just give us what we need. So that's an integration point that it's gone, which is great. And the Dotty presentation compiler, it's much easier to work with than the previous presentation compiler. So this is a quote from Martin from a few days ago, which I confirmed with him today, so I hold him accountable for this, which is he will personally work with people in the Metals and Dotty and Scala Center teams to integrate Metals with Dotty. So this is happening in couple of weeks from now, I think, there is a conference which is mostly about Scala tooling, which is Scala Sphere in Krakow, and Martin is going there, people from Virtuous Lab are there, and they're going to actually work on that thing there. So this is happening. So this puts me in a very optimistic mood, and I may be too optimistic, but I think given what I've told you today, given all the history that we have, all the pieces are coming together, everything is finally falling into the right places, and the Scala tooling perspective is as good as it's ever been. So after the pre-metals age, after the metals age, I really hope we get to the golden age of Scala tooling. I'm really optimistic about this, and I hope you will be too after this talk. So thank you very much, and thank you for listening.
Thank you, Gabriele. I think we have time for
maybe
quick
one or two questions if you
in
have.
the audience, if there are any questions. Ivano.
Thank you for your talk. My question is, are you aware or do you think there are any features that cannot be implemented with metals that currently we use in IntelliJ or mostly in IntelliJ because it has the most advanced features? Are you aware of any?
Yeah, so the answer is complicated, of course. I mean, there are features that cannot be implemented. No, we could do exactly the same thing that IntelliJ does and just copy that. But is it easy to do that with the current architecture? So some things, we explicitly decided to stay within the boundaries of LSP. Like completions, you have one kind of completion in LSP. You had three kinds of completion, I think, in IntelliJ. You just need to know the shortcuts. So IntelliJ, of course, has a much greater control over what they can implement because it's integrated. So it is not the purpose of metals to go full-blown IntelliJ, crazy amount of features. IntelliJ has been doing a great job. It's working amazingly, and it's a proven technology. So the purpose of metals is to enable developers who prefer not using an IDE and they want to just use their own editor to have a fairly comprehensive editing experience. So it's always a trade-off, right? Some people would I prefer using Vim as opposed to having that specific feature, so they are at least able to make that choice, whereas previously they essentially couldn't. So my motivation, for instance, for using metals as opposed to IntelliJ is that I work a lot with other technologies, such as TypeScript, such as Terraform files and everything, and VS Code has great support for all of this. So metals was kind of the missing piece. So that got me interested in the project, and I think it's great to keep a single editing experience across different servers, which is kind of what I was referring to at the beginning. So, of course, it would never get to IntelliJ level of integration with Scala, I think.
Okay, thank you.
Hey, thanks for the talk. One of the big difference between Bloop and Metals is that Bloop is a server, Metals is a server too, but Bloop, you have only one instance that runs, which makes it fast because it keeps the JVM warm, while Metals, you have one instance per project. Do you think it would make sense or be possible to have actually only one instance and running as a daemon or something like that?
So maybe I think there is some misunderstanding of what Metals does as opposed to Bloop. So Metals does not manage the build at all. So it doesn't have instances. What Metals does is if you don't have Bloop installed on your machine, I mean, if you have Bloop installed on your machine, you have one server and you just connect to it as a client. So Metals, in order to provide a smooth user experience, if you don't have Bloop installed on your machine, we'll run a Bloop for you in embedded mode. So whenever you open a new project with Metals, it would just run an instance of Bloop. So that goes completely away if you install Bloop on your machine. Metals would just do nothing and connect to it. So Metals, yes, so the answer is yes, you can have a single instance of Bloop and then just Metals connect to it. Metals doesn't handle anything about compilation or builds. It just knows that the meta information about the builds.
But
does it make sense? Okay.
My point was not about Bloop that much about Metal, because you have several instances of Metals running when you have
Oh, you mean the
project.
single instance of Metals?
Yes.
Okay. So Currently, we don't perceive that as a problem because if you look at the actual memory footprint of metals is in the order of the tens of megabytes. So if it spikes higher than that, it's probably because it's running in embedded mode, so it embeds a Bloop server. So if you take the Bloop server out, which is kind of the heavy part because it interacts with Scala-C, metals itself is really low on memory footprint. So no, we don't have any project for doing that in the immediate future. I mean, different technologies such as TypeScript do the same. They spin up a different server every time and it works fine.
Thank you.
Thank you for your question.
I think we're out of time for any more questions. Thank you so much again, Gabriele.
Thanks.